Hey folks, welcome to the manual testing course. Many of you may have some knowledge or idea about what software testing is. Some of you may be beginners in software testing. Some may be expert. We have designed this course in such a way that it is useful for all. We have discussed the basics of software testing as well as the more in-depth knowledge of software testing in this course. Here we will be discussing various aspects of software testing. What is software testing? How we conduct testing, types of testing, various techniques for test case design and planning, control of testing process. We will also be discussing various types of testing and various test design techniques. So let's start with the course. We have divided this course into 6 chapters. Each chapter consists of a text document with a theory, a video tutorial, and an assignment exercise to check your progress. If you have any doubts, please feel free to contact our counselor anytime during the course. The first thing that we will be discussing in this course will be the need for software testing. Why companies are spending so much money for testing their software products or projects. As there are people who know the importance of testing a software properly before its release, there are also people who think that software testing is an overhead in software development process. There are many people in the industry who think that if we create a software with care during its development period, then why should we go for test? Instead of having a testing team, if we deploy a senior programmer, then he or she will write a defect-free code. Testing is just a wastage of time and manpower, and we don't require it. Don't be surprised if you meet a person with any of these viewpoints during your testing career. We will try to answer these questions one by one and try to understand why we need software testing. The first point is a human being always do some mistake. So whatever care you take while designing a software, there are always chance that it may contain some defects, and thus software testing is required to check all these mistakes and rectify them on time. Secondly, however senior or junior a programmer is, he will remain a human and thus may make some mistakes that needs to be tested. Thirdly, and most importantly, selling a product that does not work properly to a customer can cause a huge brand image loss that will require a lot of money and time to fix, rather than having a software testing conducted on that software to make sure that it meets the expectations. So after discussing why we need software testing, the second thing that we need to understand is the software testing context. By software testing context, we mean that we need to understand if software testing is same in all situations, or does it vary from project to project or product to product. For this we need to understand the impact of a defect in a given situation or context. Not all software systems carry the same level of risk, and not all problems have the same impact when they occur. A risk is something that has not happened yet, and it may never happen. It is a potential problem. We are concerned about these potential problems, because if one of them did happen, we'd feel a negative impact. When we discuss risks, we need to consider how likely it is that the problem would occur, and the impact, if it happens. Some of the problems we encounter when using software are quite trivial, but others can be costly and damaging, with loss of money, time, or business reputation, and even may result in injury or death. For example, suppose a user interface has typographical defects. Does this matter? It may be trivial, but it could have a significant effect depending on the website and the defect. Like if my personal family tree website has my maternal grandmother's maiden name spelt wrong, I can fix it easily and only the family sees it, so this will not have much impact. But if the company website has some spelling mistakes in the text, potential customers may be put off the company as it looks unprofessional. And in the worst case, if there is a spelling mistake in a bank account number of a site, then the financial impact of such a defect would be very large. So the same spelling error may have different impact depending on the context of the software usage. So why does software defects occur? If someone makes an error or mistake in using the software, this may lead directly to a problem. The software is used incorrectly and so does not behave as we expected. However, people also design and build the software, and they can make mistakes during the design and build. These mistakes mean that there are flaws in the software itself. These are called defects, or sometimes bugs or faults. Defects in software, systems, or documents may result in failures, but not all defects do cause failures. It is not just defects that give rise to failure. Failures can also be caused by environmental conditions as well. For example, a radiation burst, a strong magnetic field, electronic fields, or pollution could cause faults in hardware or firmware. Those faults might prevent or change the execution of software. Failures may also arise because of human error in interacting with the software, perhaps a wrong input value being entered, or an output being misinterpreted. Finally, failures may also be caused by someone deliberately trying to cause a failure in a system, malicious damage. When we think about what might go wrong, we have to consider defects and failures arising from: first, errors in the specification, design, and implementation of the software and system. Second, errors in use of the system. Third, environmental conditions. Fourth, intentional damage. And last, potential consequences of earlier errors, intentional damages, defects and failures. To understand when do defects arise in a software system, let's take the following 4 cases, as represented in the figure below. Case 1. The first case in the figure is the ideal software development life cycle, SDLC. There was no mistake in gathering the requirements, no mistakes in making the design, no error in coding, and hence near-perfect software delivered to the client. Case 2. The second case is where an error was made while coding the design document. So even though there was no problem in gathering the requirements and designing the requirements, because of some error in coding the requirements, the final product not meet the expectations. Case 3. The third case is where an error was made while designing the requirements, so even though the requirements were gathered perfectly, the designer made some mistake while designing the system, and thus this mistake got propagated to the coding and to the final product. Case 4. The worst of all these cases is where the requirements were not gathered correctly. As the requirements were not correct, so the design and coding were also not correct, and in the end a software that was not meeting the expectations was delivered to the client. So from this case study, we can understand that a mistake could be made any time during the software development life cycle, and as such testing should be started as early as possible during the software development life cycle. So after understanding the cause of software defects, let us understand the cost of fixing defects. The cost of finding and fixing defects rises considerably across the life cycle. The cost of fixing defects could be understood by linking the cost with the scenarios that we have discussed in the previous section. If we draw a graph for cost of fixing a defect against the development phase in which it was found, we will get a curve, as shown in the figure. From this figure, we see that if an error is made and the consequent defect is detected in the requirements at the specification stage, then it is relatively cheap to find and fix. Similarly, if an error is made and the consequent defect detected in the design at the design stage, then the design can be corrected and reissued with relatively little expense. The same applies for construction. If, however, a defect is introduced in the requirement specification, and it is not detected until acceptance testing, or even once the system has been implemented, then it will be much more expensive to fix. This is because rework will be needed in the specification and design before changes can be made in construction, because one defect in the requirements may well propagate into several places in the design and code, and because all the testing work done to that point will need to be repeated in order to reach the confidence level in the software that we require. Testing helps us to measure the quality of software in terms of the number of defects found, the tests run, and the system covered by the tests. Testing can give confidence in the quality of the software if it finds few or no defects, provided we are happy that the testing is sufficiently rigorous. After discussing why we need software testing, causes of software defects, and the cost of fixing defect, let us discuss the main topic of this course: what is software testing? Let's use an analogy to help us understand what is testing. Driving tests. In a driving test, the examiner critically assesses the candidate's driving, noting every mistake, large or small, made by the driver under test. The examiner takes the driver through a route which tests many possible driving activities, such as road junctions of different types, control and maneuvering of the car, ability to stop safely in an emergency, and awareness of the road, other road users and hazards. Some of the activities must be tested. For example, in the UK, an emergency stop test is always carried out, with the examiner simulating the moment of emergency by hitting the dashboard, at which point the driver must stop the car quickly, safely, and without loss of control. At the end of the test, the examiner makes a judgment about the driver's performance. Has the driver passed the test or failed? The examiner bases the judgment on the number and severity of the failures identified, and also whether the driver has been able to meet the driving requirements. A single severe fault is enough to fail the whole test, but a small number of minor faults might still mean the test is passed. Many minor faults would reduce the confidence of the examiner in the quality of the driving to the point where the driver cannot pass. The format of the driving test and the conduct of the examiner are worth considering. The test is planned and prepared for. The test has known goals, assessing whether the driver is sufficiently safe to be allowed to drive by themselves without an instructor, without endangering themselves or others. There are clear pass/fail criteria, based on the number and severity of faults, but the confidence of the examiner in the driving is also taken into account. The test is therefore carried out to show that the driver satisfies the requirements for driving, and to demonstrate that they are fit to drive. The examiner looks for faults in the driving. The time for the test is limited, so it is not a complete test of the driver's abilities, but it is representative and allows the examiner to make a risk-based decision about the driver. All the drivers are tested in an equivalent way, and the examiner is neutral and objective. The examiner will log factual observations which enable a risk assessment to be made about the driving. Based on this, a driver who passes will be given a form enabling him to apply for a full driving license. A driver who fails will get a report with a list of faults and areas to improve before retaking the test. As well as observing the driver actually driving, the examiner will ask questions, or the driver will take a written exam to check their understanding of the rules of the road, road signs, and what to do in various traffic situations. Let's try to define software testing based on the analogy above. Process testing is a process rather than a single activity. There are a series of activities involved. All life cycle activities. We saw earlier that the later in the life cycle we find bugs, the more expensive they are to fix. If we can find and fix defects at the requirement stage, that must make commercial sense. We'll build the right software correctly and at a lower cost overall. So, the thought process of designing tests early in the life cycle can help to prevent defects from being introduced into code. We sometimes refer to this as verifying the test basis via the test design. The test basis includes documents such as the requirements and design specifications. Both static and dynamic testing can be done by tests, where the software code is executed to demonstrate the results of running tests, often called dynamic testing. We can also test and find defects without executing code. This is called static testing. This testing includes reviewing of documents, including source code, and static analysis. This is a useful and cost-effective way of testing. Planning. Activities take place before and after test execution. We need to manage the testing. For example, we plan what we want to do, we control the test activities, we report on testing progress and the status of the software under test, and we finalize or close testing when a phase completes. Preparation. We need to choose what testing we'll do by selecting test conditions and designing test cases. Evaluation. As well as executing the tests, we must check the results and evaluate the software under test and the completion criteria, which help us decide whether we have finished testing and whether the software product has passed the tests. Software products and related work products. We don't just test code. We test the requirements and design specifications, and we test related documents such as operation, user, and trading material. Static and dynamic testing are both needed to cover the range of products we need to test. The second part of the definition covers the sum of the objectives for testing. The reasons why we do it determine that software products satisfy specified requirements. Some of the testing we do is focused on checking products against the specification for the product. For example, we review the design to see if it meets requirements, and then we might execute the code to check that it meets the design. If the product meets its specification, we can provide that information to help stakeholders judge the quality of the product and decide whether it is ready for use. Demonstrate that software products are fit for purpose. This is slightly different to the point above. After all, the specified requirements might be wrong or incomplete. Fit for purpose looks at whether the software does enough to help the users to carry out their tasks. We look at whether the software does what the user might reasonably expect. For example, we might look at who might purchase or use the software and check that it does do what they expect. This might lead us to add a review of the marketing material to our static tests to check that expectations of the software are properly set. One way of judging the quality of a product is by how fit it is for its purpose. Detect defects. We most often think of software testing as a means of detecting faults or defects that in operational use will cause failures. Finding the defects helps us understand the risks associated with putting the software into operational use, and fixing the defects improves the quality of the products. However, identifying defects has another benefit. With root cause analysis, they also help us improve the development processes and make fewer mistakes in future work. This is a suitable definition of testing for any level of testing, from component testing through to acceptance testing, provided that we remember to take the varying objectives of these different levels of testing into account. Given this definition of program testing, an appropriate next step is determination of whether it is possible to test a program to find all of its errors. We will show you that the answer is negative, even for trivial programs. In general, it is impractical, often impossible, to find all the errors in a program. This fundamental problem will, in turn, have implications for the economics of testing, assumptions that the tester will have to make about the program, and the manner in which test cases are designed. To combat the challenges associated with testing economics, you should establish some strategies before beginning. Two of the most prevalent strategies include black box testing and white box testing, which we will explore in the next two sections. For discussing the economics of testing, let's first discuss the two broad categories into which the testing can be divided. The first one is black box testing. Black box testing is the testing that we do without the knowledge of the internal structure of the programs. In this type of testing, we are concentrated towards the input and output of the system. The second type is white box testing. White box testing is testing the software with the knowledge of the internal structure of the system. In this type of testing, we are concentrating on execution of as many program statements as possible. One important testing strategy is black box, data-driven, or input-output-driven testing. To use this method, view the program as a black box. Your goal is to be completely unconcerned about the internal behavior and structure of the program. Instead, concentrate on finding circumstances in which the program does not behave according to its specifications. In this approach, test data are derived solely from the specifications, i.e., without taking advantage of knowledge of the internal structure of the program. If you want to use this approach to find all errors in the program, the criterion is exhaustive input testing, making use of every possible input condition as a test case. Why? How many tests would you need to do to completely test a one-digit numeric field? The immediate question is, what you mean by test completely? There are 10 possible valid numeric values, but as well as the valid values, we need to ensure that all the invalid values are rejected. There are 26 uppercase alpha characters, 26 lowercase, at least 6 special and punctuation characters, as well as a blank value. So there would be at least 68 tests for this example of a one-digit field. This problem just gets worse as we look at more realistic examples. In practice, systems have more than one input field, with the fields being of varying sizes. These tests would be alongside others, such as running the tests in different environments. If we take an example where one screen has 15 input fields, each having 5 possible values, then to test all of the valid input value combinations you would need 3,517, 578, 125, 515 tests. It is unlikely that the project timescales would allow for this number of tests. This discussion shows that exhaustive input testing is impossible. Two implications of this are that, first, you cannot test a program to guarantee that it is error-free. And, second, a fundamental consideration in program testing is one of economics. That is, since exhaustive testing is out of the question, the objective should be to maximize the yield on the testing investment by maximizing the number of errors found by a finite number of test cases. Another testing strategy, white box, or logic-driven testing, permits you to examine the internal structure of the program. This strategy derives test data from an examination of the program's logic, and often, unfortunately, at the neglect of the specification. The goal at this point is to establish, for this strategy, the analog to exhaustive input testing in the black box approach. Causing every statement in the program to execute at least once might appear to be the answer, but it is not difficult to show that this is highly inadequate. Without belaboring the point, the analog is usually considered to be exhaustive path testing. That is, if you execute, via test cases, all possible paths of control flow through the program, then possibly the program has been completely tested. There are two flaws in this statement, however. One is that the number of unique logic paths through a program could be astronomically large. To see this, consider the trivial program represented in figure. The diagram is a control flow graph. Each node or circle represents a segment of statements that execute sequentially, possibly terminating with a branching statement. Each edge or arc represents a transfer of control, branch, between segments. The diagram, then, depicts a 10 to 20 statement program consisting of a do loop that iterates up to 20 times. Within the body of the do loop is a set of nested if statements. Determining the number of unique logic paths is the same as determining the total number of unique ways of moving from point A to point B, assuming that all decisions in the program are independent from one another. This number is approximately 1014, or 100 trillion. Since most people have a difficult time visualizing such a number, consider it this way: if you could write, execute, and verify a test case every 5 minutes, it would take approximately 1 billion years to try every path. If you were 300 times faster, completing a test once per second, you could complete the job in 3.2 million years, give or take a few leap years and centuries. Of course, in actual programs every decision is not independent from every other decision, meaning that the number of possible execution paths would be somewhat less. On the other hand, actual programs are much larger than the simple program depicted in Figure 1.3. Hence, exhaustive path testing, like exhaustive input testing, appears to be impractical, if not impossible. Let's discuss the principles of testing first. A necessary part of a test case is a definition of the expected output or result. This obvious principle is one of the most frequent mistakes in program testing. If the expected result of a test case has not been predefined, chances are that a plausible, but erroneous, result will be interpreted as a correct result because of the phenomenon of the eye seeing what it wants to see. Therefore, a test case must consist of two components: 1. A description of the input data to the program. 2. A precise description of the correct output of the program for that set of input data. Second principle is a programmer should avoid attempting to test his or her own program. Any writer knows, or should know, that it's a bad idea to attempt to edit or proofread his or her own work. You know what the piece is supposed to say and may not recognize when it says otherwise. And you really don't want to find errors in your own work. The same applies to software authors. Another problem arises with a change in focus on a software project. After a programmer has constructively designed and coded a program, it is extremely difficult to suddenly change perspective to look at the program with a destructive eye. Third principle is a programming organization should not test its own programs. The argument here is similar to the previous argument. A project or programming organization is, in many senses, a living organization with psychological problems similar to those of individual programmers. Furthermore, in most environments, a programming organization or a project manager is largely measured on the ability to produce a program by a given date and for a certain cost. One reason for this is that it is easy to measure time and cost objectives, but it is extremely difficult to quantify the reliability of a program. Therefore, it is difficult for a programming organization to be objective and test in its own programs, because the testing process, if approached with the proper definition, may be viewed as decreasing the probability of meeting the schedule and the cost objectives. The fourth principle is thoroughly inspect the results of each test. This is probably the most obvious principle, but again it is something that is often overlooked. We've seen numerous experiments that show many subjects failed to detect certain errors, even when symptoms of those errors were clearly observable on the output listings. Put another way, errors that are found on later tests are often missed in the results from earlier tests. The fifth principle is test cases must be written for input conditions that are invalid and unexpected, as well as for those that are valid and expected. There is a natural tendency, when testing a program, to concentrate on the valid and expected input conditions, at the neglect of the invalid and unexpected conditions. Many errors that are suddenly discovered in production programs turn up when the program is used in some new or unexpected way. Therefore, test cases representing unexpected and invalid input conditions seem to have a higher error detection yield than do test cases for valid input conditions. Next principle is examining a program to see if it does not do what it is supposed to do is only half the battle. The other half is seeing whether the program does what it is not supposed to do. This is a corollary to the previous principle. Programs must be examined for unwanted side effects. For instance, a payroll program that produces the correct paychecks is still an erroneous program if it also produces extra checks for non-existent employees, or if it overwrites the first record of the personnel file. The seventh principle is avoid throwaway test cases, unless the program is truly a throwaway program. This problem is seen most often with interactive systems to test programs. A common practice is to sit at a terminal and invent test cases on the fly, and then send these test cases through the program. The major problem is that test cases represent a valuable investment that, in this environment, disappears after the testing has been completed. Whenever the program has to be tested again, for example, after correcting an error or making an improvement, the test cases must be reinvented. More often than not, since this reinvention requires a considerable amount of work, people tend to avoid it. Therefore, the retest of the program is rarely as rigorous as the original test, meaning that if the modification causes a previously functional part of the program to fail, this error often goes undetected. Saving test cases and running them again after changes to other components of the program is known as regression testing. Principle number 8 is do not plan a testing effort under the tacit assumption that no errors will be found. This is a mistake project managers often make and is a sign of the use of the incorrect definition of testing, that is, the assumption that testing is the process of showing that the program functions correctly. Once again, the definition of testing is the process of executing a program with the intent of finding errors. Next one is the probability of the existence of more errors in a section of a program is proportional to the number of errors already found in that section. Another way of stating this principle is to say that errors tend to come in clusters, and that, in the typical program, some sections seem to be much more prone to errors than other sections, although nobody has supplied a good explanation of why this occurs. The phenomenon is useful in that it gives us insight or feedback in the testing process. If a particular section of a program seems to be much more prone to errors than other sections, then this phenomenon tells us that, in terms of yield on our testing investment, additional testing efforts are best focused against this error-prone section. The last one, testing, is an extremely creative and intellectually challenging task. It is probably true that the creativity required in testing a large program exceeds the creativity required in designing that program. We already have seen that it is impossible to test a program sufficiently to guarantee the absence of all errors. Methodologies discussed later in this book let you develop a reasonable set of test cases for a program, but these methodologies still require a significant amount of creativity. The fundamental testing processes starts with test planning and continue through to test closure. As we have seen, although executing tests is important, we also need a plan of action and a report on the outcome of testing. Project and test plan should include time to be spent on planning the tests, designing test cases, preparing for execution, and evaluating status. The idea of a fundamental test process for all levels of test has developed over the years. Whatever the level of testing, we see the same type of main activities happening, although there may be a different amount of formality at the different levels. For example, component tests might be carried out less formally than system tests in most organizations with a less documented test process. The decision about the level of formality of the processes will depend on the system and software context, and the level of risk associated with the software. So we can divide the activities within the fundamental test process into the following basic steps: planning and control, analysis and design, implementation and execution, evaluating exit criteria and reporting, test closure activities. During test planning, we make sure we understand the goals and objectives of the customers, stakeholders, and the project, and the risks which testing is intended to address. This will give us what is sometimes called the mission of testing, or the test assignment. Based on this understanding, we set the goals and objectives for the testing itself, and derive an approach and plan for the tests, including specification of test activities. To help us, we may have organization or program test policies, and a test strategy. Test policy gives rules for testing, e.g., we always review the design documents. Test strategy is the overall high-level approach, e.g. system testing is carried out by an independent team reporting to the program quality manager. Test planning has the following major tasks, given approximately in order, which help us build a test plan, determine the scope and risks, and identify the objectives of testing. We consider what software, components, systems, or other products are in scope for testing, the business, product, project, and technical risks which need to be addressed, and whether we are testing primarily to uncover defects, to show that the software meets requirements, to demonstrate that the system is fit for purpose, or to measure the qualities and attributes of the software. Determine the test approach, techniques, test items, coverage, identifying and interfacing with the teams involved in testing, testware. Implement the test policy or the test strategy. We mentioned that there may be an organization or program policy and strategy for testing. If this is the case, during our planning we must ensure that what we plan to do adheres to the policy and strategy, or we must have agreed with stakeholders and documented a good reason for diversion from it. Determine the required test resources, e.g. people, test environment, PCs, schedule test analysis and design tasks, test implementation, execution, and evaluation. Determine the exit criteria. Management of any activity does not stop with planning it. We need to control and measure progress against the plan. So, test control is an ongoing activity. We need to compare actual progress against the planned progress and report to the project manager and customer on the current status of testing, including any changes or deviations from the plan. We'll need to take actions where necessary to meet the objectives of the project. Such actions may entail changing our original plan, which often happens when different groups perform different review and test activities within the project. The planning and control needs to happen within each of those groups, but also across the groups to coordinate between them, allowing smooth handoffs between each stage of testing. Test planning takes into account the feedback from monitoring and control activities which take place throughout the project. Test control has the following major tasks: measure and analyze the results of reviews and testing. We need to know how many reviews and tests we have done. We need to track how many tests have passed and how many failed, along with the number, type, and importance of the defects reported. Monitor and document progress, test coverage, and exit criteria. It is important that we inform the project team how much testing has been done, what the results are, and what conclusions and risk assessment we have made. We must make the test outcome visible and useful to the whole team. provide information on testing. We should expect to make regular and exceptional reports to the project manager, project sponsor, customer, and other key stakeholders to help them make informed decisions about project status. We should also use the information we have to analyze the testing itself. Initiate corrective actions. For example, tighten exit criteria for defects fixed, ask for more effort to be put into debugging, or prioritize defects for fixing test blockers. Make decisions based on the measures and information gathered during testing, and any changes to business and project risks, or our increased understanding of technical and product risks, will make decisions, or enable others to make decisions, to continue testing, to stop testing, to release the software, or to retain it for further work, for example. The next topic in test control and monitoring is test analysis and design. Test analysis and design is the activity where general testing objectives are transformed into tangible test conditions and test designs. During test analysis and design, we take general testing objectives identified during planning and build test designs and test procedures, scripts. Test analysis and design has the following major tasks, in approximately the following order. Review the test basis, such as the product risk analysis, requirements, architecture, design specifications, and interfaces, examining the specifications for the software we are testing. We use the test basis to help us build our tests. We can start designing certain kinds of tests, called black box tests, before the code exists, as we can use the test basis documents to understand what the system should do once built. As we study the test basis, we often identify gaps and ambiguities in the specifications, because we are trying to identify precisely what happens at each point in the system, and this also prevents defects appearing in the code. Identify test conditions based on analysis of test items, their specifications, and what we know about their behavior and structure. This gives us a high-level list of what we are interested in testing. Design the tests using techniques to help select representative tests that relate to particular aspects of the software which carry risks or which are of particular interest based on the test conditions, and going into more detail. Evaluate testability of the requirements and system. The requirements may be written in a way that allows a tester to design tests. For example, if the performance of the software is important, that should be specified in a testable way. If the requirements just say, the software needs to respond quickly enough, that is not testable, because quick enough may mean different things to different people. A more testable requirement would be, the software needs to respond in 5 seconds, with 20 people logged on. The testability of the system depends on aspects such as whether it is possible to set up the system in an environment that matches the operational environment, and whether all the ways the system can be configured or used can be understood and tested. Design the test environment setup and identify any required infrastructure and tools. This includes testing tools and support tools such as spreadsheets, word processors, project planning tools, and non-IT tools and equipment, everything we need to carry out our work. After analysis and design, the next activity would be test implementation and execution. During test implementation and execution, we take the test conditions and make them into test cases and testware and set up the test environment. This means that, having put together a high-level design for our tests, we now start to build them. We transformed our test conditions into test cases and procedures, other testware such as scripts for automation. We also need to set up an environment where we will run the tests and build our test data. Setting up environments and data often involves significant time and effort, so you should plan and monitor this work carefully. Test implementation and execution have the following major tasks, in approximately the following order. Implementation. Develop and prioritize our test cases, and create test data for those tests. We will also write instructions for carrying out the tests, test procedures. Create test suites from the test cases for efficient test execution. A test suite is a logical collection of test cases which naturally work together. Test suites often share data and a common high-level set of objectives. We'll also set up a test execution schedule. Implement and verify the environment. We make sure the test environment has been set up correctly, possibly even running specific tests on it. Execution. 1. Execute the test suites and individual test cases, following our test procedures. We might do this manually or by using test execution tools, according to the planned sequence. 2. Log the outcome of test execution and record the identities and versions of the software under test, test tools and testware. We must know exactly what tests we used against what version of the software. We must report defects against specific versions, and the test log we keep provides an audit trail. 3. Compare actual results, what happened when we ran the tests, with expected results, what we anticipated would happen. 4. Where there are differences between actual and expected results, report discrepancies as incidents. We analyze them to gather further details about the defect, reporting additional information on the problem, identify the causes of the defect, and differentiate between problems in the software and other products under test, and any defects in test data, in test documents, or mistakes in the way we executed the test. We would want to log the latter in order to improve the testing itself. 5. Repeat test activities as a result of action taken for each discrepancy. We need to re-execute tests that previously failed in order to confirm a fix, confirmation testing, or retesting. We execute corrected tests and suites if there were defects in our tests. We test corrected software again to ensure that the defect was indeed fixed correctly, confirmation test, and that the programmers did not introduce defects in unchanged areas of the software, and that fixing a defect did not uncover other defects, regression testing. The next activity in test planning and control is evaluating the exit criteria and reporting. Evaluating exit criteria is the activity where test execution is assessed against the defined objectives. This should be done for each test level, as for each we need to know whether we have done enough testing. Based on our risk assessment, we'll have set criteria against which we'll measure enough. These criteria vary for each project and are known as exit criteria. They tell us whether we can declare a given testing activity or level complete. We may have a mix of coverage or completion criteria, which tell us about test cases that must be included, acceptance criteria, which tell us how we know whether the software has passed or failed overall, and process exit criteria, which tell us whether we have completed all the tasks we need to do. Exit criteria should be set and evaluated for each test level. Evaluating exit criteria has the following major tasks. 1. Check test logs against the exit criteria specified in test planning. 2. Assess if more tests are needed, or if the exit criteria specified should be changed. We may need to run more tests if we have not run all the tests we designed, or if we realize we have not reached the coverage we expected, or if the risks have increased for the project. We may need to change the exit criteria to lower them if the business and project risks rise in importance and the product or technical risks drop in importance. Note that this is not easy to do and must be agreed with stakeholders. 3. Write a test summary report for stakeholders. It is not enough that the testers know the outcome of the test. All the stakeholders need to know what testing has been done and the outcome of the testing in order to make informed decisions about the software. The last activity in test planning and control would be test closure. During test closure activities, we collect data from completed test activities to consolidate experience, including checking and filing testware and analyzing facts and numbers. We may need to do this when software is delivered. We also might close testing for other reasons, such as when we have gathered the information needed from testing, when the project is cancelled, when a particular milestone is achieved, or when a maintenance release or update is done. Test closure activities include the following major tasks. 1. Check which planned deliverables we actually delivered, and ensure all incident reports have been resolved through defect repair or deferral. For deferred defects, in other words those that remain open, we may request a change in a future release. We document the acceptance or rejection of the software system. 2. finalize and archive testware, such as scripts, the test environment, and any other test infrastructure, for later reuse. It is important to reuse whatever we can of testware. We will inevitably carry out maintenance testing, and it saves time and effort if our testware can be pulled out from a library of existing tests. It also allows us to compare the results of testing between software versions. 3. Hand over testware to the maintenance organization, who will support the software and make any bug fixes or maintenance changes for use in confirmation testing and regression testing. This group may be a separate group to the people who build and test the software. The maintenance testers are one of the customers of the development testers. They will use the library of tests. 4. Evaluate how the testing went and analyze lessons learned for future releases and projects.